So let's start looking at the different types of organometallic reactions. So we know that those organometallic complexes, obviously they do exist. We know how to count how many electrons we have for each of them. Let's introduce the different categories of organometallic reactions. So what's one of the really very useful point here is that just by looking at the wording, we know exactly what those reactions are, what are they pretty much going to lead to. The first one that we're going to introduce is the ligand substitution. So we'll cover substitution, so we are substituting one ligand for another. We're going to be looking at addition, so we can add ligands to a molecule, and we're going to do this in different ways, or I'm going to present to you that we can do an addition in different ways. We can also have ligands migrating, or groups of elements migrating, and finally we can also eliminate at least one element from a complex. So we'll go through substitution reactions, oxidative addition reactions, migration reactions, and finally elimination reactions. And those are the four main types of organometallic reactions that are very useful for the purpose of this course, especially in light of looking at catalysis. So let's start with the first one, the ligand substitution. A ligand substitution always happens, and that's pretty much is the key. It always happens, and I will add, it can't happen if there is no light added to the reaction or no heat added to the reaction. So it has to happen by photochemical or thermal activation. If there's no photons, so no light, and if there's no heat, so no thermal activation, we will not have a ligand substitution. In order for us to know that we either have photochemical or thermal activation, we either have the little H nu here that obviously says that we have an input of energy through light, or sometimes you would actually see a little triangle that means that we have heat. We have a heat input in the reaction. There are two different ways that we can substitute a ligand, and most of the time the ligand that is being substituted is carbonyl, because it's the main type of ligands obviously in organometallic complexes. So there's two ways to do this substitution. So when I say substitution, that means that I'm going to substitute, I'm going to replace one of the carbonyl ligand with a different ligand. So if we start with the direct substitution, so if we have a direct reaction of a complex that is a metal carbonyl complex and a ligand, right? So this is a direct substitution here. I'm actually going to directly replace one of these 5 carbonyls here, just one of them, with a ligand that happens to be here, right, an alkene, right, with a double bond, right? So that's my ethene, that is an eta-2 ethyl, ethene ligand, right? So what we start with here is, so we have iron 0, right, 8 electrons, we have 5 carbonyls, so 8 plus 10, that's 18. So we start with an 18 electron complex. That 18 electron complex, so 5 carbonyls, which means that we have a trigonal bipyramidal complex to start with, right? When we add the eta-2 ethene to this complex, that means that we're going to take one of the carbonyl, it's going to get kicked out, and it's going to be replaced with my ethene, right? So at the end, what's going to happen is that I'm going to have one less carbonyl, so 4 carbonyl instead of 5, and I'm going to have my eta-2 ethene that will be added, okay? When you do a substitution, normally, right, the number of electrons that you have in your starting complex is the same number of electrons that you have in the product. Let's confirm that. So if we think about the eta-2 ethene provides 2 electrons. My 4 carbonyls, they provide obviously 8 electrons, right? So 8 plus 2, that's 10, plus 8 from the iron, that's 18, right? So my starting complex has 18 electrons, my product has 18 electrons also. It's also trigonal bipyramidal, right? I've just done a substitution. I am not changing the total number of ligands around my ion. So what I end up with is a trigonal bipyramidal complex that has 1, 2, 3, 4 carbonyls and my eta 2 ethene. Okay, so remember to really signify that we are having an eta 2 hapticity. I have to have that double bond, and then the bond from the ion to the middle, to the center of that double bond. Okay, trigonal bipyramidal, trigonal bipyramidal. That's a direct substitution, right? I did not use any intermediate reaction here. Well, sometimes when one of these ligands is very difficult to kick out for some complexes, we actually have to go through an intermediate step. And that intermediate step means that we're going to at first replace the carbonyl with a more labile ligand. Labile ligand means that they are very easily kicked out, which means that if I can replace one of these carbonyl here with, for example, a THF, tetrahydrofuran, which is a good solvent, or a methyl cyanide, I will have then more, I will have more chance, if I can put it this way, to be able to kick out that ligand and then replace that ligand with an incoming different ligand. Okay, so sometimes we can do a direct substitution. We have to go through the attachment of a more labile ligand first, and then we proceed with our ligand substitution. In this example, what do we have? We have a molybdenum carbonyl complex, again, 18 electrons to start with, right? I cannot add anything to it. I can only substitute one of these carbonyls. When I substitute one of these carbonyls, the way I will indicate to you that we have to go through that first intermediate step is to actually, for me to have THF, right? If you see THF or if you see methyl cyanide on the top of the arrow, that means that this is a reaction that will be a two-step reaction. The first step will be the replacement of the carbonyl, of one of the carbonyls with THF, which we have here, and then we can add the incoming ligand, which happens to be, in this case, the triphenylphosphine. So this THF is labile. It's going to be kicked out very quickly and easily, and it's going to be replaced with my triphenylphosphine. Okay. We still have 18 electrons, right? Triphenylphosphine provides 2 electrons, 2 plus 10, that's 12, plus 6, that's 18. So I still end up with 18 electrons. I started with an octahedral complex. I still end up with an octahedral complex. Okay, so I really need to be careful in terms of what is given to you on the top of the arrow here. If I just have the input of light or the input of heat and no THF or no methyl cyanide, that means that I have a direct substitution. If you see that I have on the top of the arrow THF or methyl cyanide and my input of heat or energy, that means that I have to go through an intermediate step, which will be, first of all, the replacement of a carbonyl with THF, and then the replacement of the THF or the methyl cyanide with the incoming ligand, which happens to be triphenylphosphine here. Okay, so we have to look carefully at what's given to us to be able to know, are we going to go through a direct substitution, or are we going to be using here a more labile ligand first? Okay, so next time we'll look at the oxidative addition. There's actually 3 different ways to do that depending on what we start with. So what's really important in determining the products of these different organometallic reactions is to really pinpoint what we start with so that we can determine what the product will be. And once we are kind of getting trained to doing this, then the products are pretty much always going to follow the same pattern. Okay, I'll see you on Wednesday. Have a good one. Have a great day.